Welcome to this lesson about some aspects of Earth's reflectivity, and in particular, some dynamic changes in reflectivity and feedbacks involving reflectivity. As you know, some surfaces are more reflective than others. Clean ice and clouds are highly reflective. Ocean water and dark forests are less reflective. Tiny particles and droplets in the atmosphere can be reflective, like sulfate aerosols from volcanoes and fossil fuel burning, or particles of sea salt whipped into the atmosphere by breaking waves. Or particles in the atmosphere can be less reflective, like soot from forest fires. The nature of Earth's surface and the stocks of different reflective materials in the atmosphere can change over time. In this lesson, we'll take a look at some examples and get into a few of the feedbacks in Earth's climate system that involve reflectivity. There are, of course, far more out there in the world than we'll be able to talk about here. Here's an example of an interaction between different parts of the climate system that changes reflectivity. This is an image from NASA, and it's a picture of snow in the mountains of Colorado. And what you can see is that the surface of the snow has a lot of dust on it. This is dust that's blowing in from deserts in the western United States, and over time, the dust influx has increased, which darkens the snow surfaces, which then absorb more solar energy, and then they melt faster. The faster melting then changes the seasonal availability of water for the ecosystems downstream from this melting snowpack, releasing it earlier in the year with various biological ramifications. So this is just an example of how reflectivity can influence and also be influenced by other parts of the climate system. Reflectivity is one of the places in Earth's climate system where we humans have opportunities to intervene and change energy flows. One way we do it is by emitting things into the atmosphere. We emit things like reflective sulfates when we burn coal. We also emit black soot, which is not reflective, and when it lands on highly reflective surfaces like ice, it decreases the reflectivity of the ice, like in this Colorado example with dust. We also change the nature of land surfaces by clearing forests for agriculture, which changes the surface from dark to lighter, or by abandoning more reflective agricultural land on which forests then grow back. In some places, we actively plant forests. As we think about mitigation options to counter warming, it's worth evaluating those that make Earth more reflective. We saw earlier that about 30% of incoming solar radiation gets reflected right back to space, both by reflective things in the atmosphere and reflective things on Earth's surface. Reflection in the atmosphere accounts for more watts per meter squared going back to space than does reflection off the surface. And clouds alone are responsible for about half the total reflection. So clouds are important. But first, let's have a look at the surface without the clouds. This is an image of Earth with the clouds removed. Notice the dark ocean, the white ice on Antarctica, Greenland, and other high northern latitudes. You can even see some of the ice on mountain glaciers if you look closely. Notice the dark green forests and the light-colored deserts. You can see there are bands of forests dominating at some latitudes and bands of deserts dominating at other latitudes. These patterns are largely related to atmospheric circulation and regional temperature and precipitation. Here's a beautiful boundary between forest and desert in Africa. This is a boundary that shifts a little bit over time. So let's just consider some what-if scenarios. What if the forested area expanded a little bit northward into the desert area? What would happen to the reflectivity of this region? If in this part of the world, the area covered by forest expanded and that covered by desert decreased, then overall the surface would be darker and reflectivity would decrease. If this were the only thing going on in the world, the surface would absorb more incoming solar radiation and it would warm up. You can imagine all sorts of changes in Earth's surface that would alter overall albedo. What would happen, for example, if sea level rose or fell? The oceans are generally darker than the land surface, so sea level can alter surface reflectivity too. Think about other possible swaps, their effects on reflectivity and ultimately on temperature. In an earlier lesson, we've already seen at least one feedback involving reflectivity. That's the ice albedo feedback. And that one is an amplifying feedback. Here we're going to have a look at some others, including both amplifying and stabilizing feedbacks. Let's look at a feedback involving vegetation reflectivity. This one actually involves snow as well. We saw earlier that the northern high latitudes are warming faster than other parts of the world. So warmer temperatures up there make it possible for taller shrubs and even trees to start gaining a foothold and expanding into tundra ecosystems. The taller, darker vegetation sticks up farther above the snow, and this area then becomes less reflective, absorbs more solar energy, and that all helps promote warming. This is an amplifying feedback because the response helps push the system in the same direction as the perturbation, which was an initial warming. Heading into the atmosphere now, since that's where a lot of the reflection takes place, particularly by clouds, but also aerosols like dust and sulfuric acid droplets. Some clouds are highly reflective and others are less reflective. And also different particles are more or less reflective, depending on what they are. About clouds. Characteristics that make particular clouds better reflectors are first, cloud thickness. Thick clouds are more reflective than thin clouds. Second, there's droplet size. Small droplets are more reflective than large droplets. And third, there's droplet concentration. The more droplets present in a given volume of the atmosphere, the more reflective the clouds. One way to get smaller droplet sizes and potentially higher concentrations is where there are lots of aerosols in the atmosphere, which act as tiny nucleation surfaces for the droplets. And when a cloud is composed of smaller droplets, those small droplets tend not to rain out as readily as larger droplets. So the cloud's lifetime in the atmosphere has a chance to be extended too, which gives it a chance to reflect more solar radiation. Clouds are complicated. Feedbacks involving clouds are one of the parts of the climate system that's least well understood right now. So we'll have a look at a couple of what-if scenarios in order to think about the processes involved in cloud feedbacks. But the devil is really in the details when we're dealing with clouds. So imagine a perturbation toward warming, which means that overall, there'd be more water in the atmosphere. Take a look at this loop and decide what happens next, where the question mark is, and therefore whether this is an amplifying feedback or a stabilizing feedback. So we have more water in the atmosphere. And if that extra water is in liquid or ice form, say as droplets or ice crystals in clouds, then cloud cover would increase. Then overall cloud reflectivity would increase. More incoming solar radiation would get reflected, and all that would counteract the warming. This would be a stabilizing feedback. Another of the possibilities is that a perturbation toward warming translates into more of the water present in the atmosphere being there in the form of water vapor, not as droplets or ice crystals. At warmer temperatures in general, a greater proportion of the water is in vapor form. With warming, liquid droplets in the atmosphere might actually evaporate. In this case, there'd be less cloud cover, lower reflectivity, and the warming would be amplified by this type of response. In addition, the water vapor is a greenhouse gas, but that's a different feedback. From recent research, it's looking like cloud feedbacks in a warming world are likely to be overall amplifying. But the ranges of possibility include clouds acting as a net stabilizing feedback or having little feedback effect. It's an area of active research. We've barely scratched the surface of reflectivity issues in the climate system here. Ultimately, just like in all the other parts of the climate system, it's changes in the stocks of things that can influence energy flows. If the stock of clouds or reflective particles or forests or ocean water changes, the amount of energy reflected directly back to space will also change and will alter Earth's energy balance. For each one of the reflective players, we'd have to take a close look at the processes involved in inflow and outflow for that particular substance. We'd have to look at which one of the flows is winning over time and how they're interacting with the other parts of the system.